The birth of the Sun and the Solar System, the cosmic context. 4.6 billion years ago, deep within space, in the Orion arm of our Milky Way Galaxy, there floated a vast molecular cloud. A cold, immense region of gas and dust. It was composed mostly of hydrogen and helium, with trace amounts of heavier elements and cosmic dust grains. The cloud was calm and quiet, but the universe had other plans. The ingredients. This cloud was the ancestor of our solar system, the pre-solar nebula, or solar nebula. Its elements came from ancient stars that had reached the end of their life cycles, exploding as supernovae and scattering their inner materials into space. Those stardust grains would become the foundation of our Earth and even of our own bodies. Gravitational collapse. Somewhere nearby, perhaps a supernova explosion or another cosmic disturbance sent a shockwave through the nebula, slightly compressing part of it. That small disturbance was the seed of creation. As certain regions became denser, gravity took over, pulling more and more material inward. This self-reinforcing collapse is known as gravitational collapse. As gravity tightened its grip, gas and dust began to flow toward the center. The clouds started to shrink and spin, the beginning of the solar system's birth. The birth of the Sun, the protostar and the disk. As the cloud contracted, its rotation sped up, just like an ice skater spinning faster by pulling in their arms. The spinning cloud flattened into a disk, the protoplanetary disk, with most of the mass concentrated at the center. That hot, dense center became the protostar, the Sun's early form. Under immense gravitational pressure, the temperature at the core rose dramatically. The protostar was not yet a true star. It shone only because of the heat released by gravitational contraction. For about 10 million years, the collapse continued. When the core temperature reached 15 million Kelvin, hydrogen atoms began to fuse into helium, releasing enormous amounts of energy. At that exact moment, roughly 4.6 billion years ago, the Sun was born. The outward pressure from nuclear fusion balanced the inward pull of gravity, creating a stable equilibrium. Our Sun had entered the main sequence phase, becoming a steady, shining star. The making of planets. Accretion and coagulation. Once the newborn Sun began to radiate light and solar wind, the remaining gas and dust in the surrounding disk started to coalesce into planets. The solar wind blew away lighter gases from the inner regions, leaving behind heavier materials like silicates and metals. Tiny dust grains collided, stuck together, and slowly grew into small rocky clumps, a process called accretion. These clumps became planetesimals and eventually protoplanets, the building blocks of the planets. The frost line and gas giants. At a certain distance from the Sun, called the frost line, temperatures were low enough for volatile compounds like water vapor, ammonia, and methane to freeze into ice. Inside the frost line, the inner solar system, only rocky and metallic materials could survive the heat. Here formed the terrestrial planets, Mercury, Venus, Earth, and Mars. Beyond the frost line, the outer solar system, icy materials were abundant, allowing protoplanets to grow massive enough to attract huge amounts of hydrogen and helium gas. These became the gas giants, Jupiter, Saturn, Uranus, and Neptune. The stabilized solar system. Planetary migration. Before reaching their current orbits, the planets underwent a chaotic phase. The massive gas giants, especially Jupiter, likely shifted their positions, a process known as planetary migration. This rearrangement caused countless asteroids and comets to be scattered from their original paths. the Late Heavy Bombardment, LHB. Around 3.9 billion years ago, the inner solar system experienced a violent era known as the Late Heavy Bombardment. Asteroids and comets rained down on the young planets. The craters still visible on the Moon and other rocky worlds are remnants of this turbulent time. These impacts may have delivered water and essential elements to Earth, the seeds of life itself. The solar system today. After 4.5 billion years, our solar system has reached a stable configuration. The Sun, the central star whose gravity binds the entire system together. The inner planets, Mercury, Venus, Earth, and Mars, small, rocky worlds. The asteroid belt, a vast ring of rocky debris between Mars and Jupiter. The outer planets, Jupiter, Saturn, Uranus, and Neptune, the gas giants. The Kuiper belt, a region beyond Neptune filled with icy bodies, including Pluto. The Oort cloud, a distant spherical shell of frozen comets surrounding the system. From a swirling cloud of dust to a luminous star and life-bearing worlds, this is one of the universe's most extraordinary and perhaps most common stories. A cosmic dance spanning billions of years that created our remarkable solar system. Cosmic raw materials. The Great Void. Look out into space, billions of stars, galaxies, and endless darkness. Yet this void is not truly empty. Around 4.6 billion years ago, where our solar system now lies, there existed a vast, cold, dark molecular cloud, the pre-solar nebula. This nebula was immense, stretching across dozens of light years. It was made mostly of hydrogen and helium, the two lightest elements forged in the Big Bang. But most crucial were the tiny traces of heavier elements and cosmic dust grains. Cosmic synthesis, the legacy of stars. Where did those heavier elements come from? The answer lies deep in the universe's history. Our Sun is what astronomers call a population 1 star, meaning it was born from material enriched by earlier generations of stars. The first stars, population 3, contained only hydrogen and helium. When they exploded as supernovae, they created and scattered heavier elements like carbon, oxygen, silicon, and iron. Our pre-solar nebula was made of this stellar ash. Those same atoms now make up Earth, water, and our very bodies. The fall of stability. The molecular cloud drifted silently through space for millions of years, stable and cold, until a great event disrupted it. A nearby supernova explosion likely sent a shockwave through the cloud, compressing it and triggering gravitational collapse. Once density in a region increased beyond a critical threshold, gravity took control, pulling in more and more matter. The more it pulled, the stronger it became, accelerating the collapse. The self-sustaining process of gravitational collapse had begun. The birth of a star, from protostar to stability. Spinning up and disk formation. As the collapse progressed, the nebula's faint initial rotation sped up due to the conservation of angular momentum. Like a spinning skater drawing in their arms, the cloud began to flatten along its poles, forming a giant rotating accretion disk. Nearly 99.8% of the mass collected at the center, becoming the Sun, while the remaining 0.2% spread out in the disk, giving rise to planets, moons, asteroids, and comets. The central mass, the protostar, glowed faintly from the heat of gravitational compression. The temperature gradient. Each part of the disk had a different temperature. Near the protostar, it was scorching hot. Farther out, it grew cold. This temperature difference shaped the future of the solar system. Inner disk. Only metals, iron, nickel, and silicates could remain solid. Gases evaporated away. Frost line, 3 to 5 AU. Beyond this boundary, temperatures dropped below the freezing point of water, allowing ices like water, methane, and ammonia to condense. Nuclear ignition. The sun lights up. As the protostar contracted, its temperature and pressure skyrocketed. When the core reached 15 million Kelvin, nuclear fusion began. Hydrogen nuclei fused into helium, releasing massive energy. At that instant, outward pressure from fusion balanced inward gravity, and a stable, shining sun was born. The birth of planets, accretion, and differentiation. From dust to pebbles. With the sun ignited, planet formation began in earnest. Microscopic dust grains clumped together through electrostatic forces, forming pebbles, rocks, and eventually planetesimals several kilometers wide. Once large enough, their own gravity helped them attract more material, growing rapidly into protoplanets. The rocky worlds, inner planets. Inside the frost line, only rock and metal could form solids. Repeated collisions built 4 terrestrial planets: Mercury, Venus, Earth, and Mars. Giant impacts. Growth was violent. Massive collisions merged worlds. The Moon likely formed when a Mars-sized body struck the young Earth. Differentiation. As planets grew hot, heavier elements like iron sank to their cores, while lighter silicates rose to form mantles and crusts. The giants beyond the line, outer planets. Beyond the frost line, abundant ices allowed rapid formation of large rocky cores. Once these cores reached approximately 10 to 30 Earth masses, they gravitationally captured vast amounts of hydrogen and helium gas. Jupiter and Saturn became gas giants. Uranus and Neptune, forming farther away, captured less gas and more ice, becoming ice giants. Conclusion. The cosmic wonder. The birth of the Sun in the solar system is an epic tale, a story of a cold cloud stirred by a star's death, shaped by gravity's relentless pull, and refined by countless collisions over billions of years. Today we live in this calm, stable solar system, seeking to understand its beginnings. We are made of the same stardust that once drifted through dark space. The sun still burns its hydrogen. Planets still trace their ancient orbits. And we, children of stars, continue to gaze upward, searching for our cosmic origins. You have just heard the birth of the sun and the solar system.